This is the first instalment in the replacement lectures for the Good Friday and Anzac Day public holidays. I'm going to break these up into some smaller segments than full lectures would be, and also slow down and show some Excel stuff along the way as well, which we normally don't have time for in lectures. So I'll break these into a few smaller segments and encourage you at the end of each one to grab the Excel files that I'm using and to reproduce the analysis that I've done, or in fact stop the videos as I'm doing them and follow along and produce the analysis as well. I think that would be a good way to enhance your understanding of what's going on. So we've already started talking about, in Lecture 13, the process of hypothesis testing for a mean, and in particular we started talking about upper tail tests. So the story that we had to this point was that there was a simple random sample of some observations x1 up to xn that were gathered from some population, and we're interested in trying to estimate and test a hypothesis about this population mean mu, which is the expected value of the x's. And we have a sample mean, x bar, the sample mean of these observations, which we treat as being an estimator of mu. The hypotheses in their most general form for an upper-tailed test can be specified like this. So we have a null hypothesis, which always has this form of the population mean being equal to something. And I've just written m here. So that could be any number which will be given in the question or by the context or whatever it is. Okay, so this will be a known number, and we'll see examples as we go along. Some number will go in here, and this null hypothesis is always the equality, that is equal to some number, and the alternative hypothesis is one of the three possibilities: greater than for an upper tail test, less than for a lower tail test, and not equals to for a two-tail test. And in these lectures we're going to have a look at each one of those possibilities. So for now we're looking at the upper tail test because we have this greater than in the alternative hypothesis. And as we've discussed already, and we'll see examples, the type of alternative hypothesis that you specify has to be worked out on the basis of what's in the question that you're trying to answer. So that's a question of translating the words into the appropriate kind of alternative hypothesis. Alright, you have some data, right, some x1 up to xn, and here are the steps that you go through in order to test this hypothesis and make a decision about whether you're going to reject this null in favour of this alternative hypothesis or not. The t-statistic is what we use for this purpose, which is the difference between the sample mean, x bar, and the value which is specified under the null hypothesis. So basically we're testing to see how far the estimate of the mean is away from the hypothesized value. And that difference is scaled or standardized by the standard error of the x bar, the standard error being the standard deviation s of the observations divided by the square root of n, where n is the sample size used to calculate the x bar. Okay, so that's our t-statistic. We've seen that before. And we put in quite a bit of work in figuring out what the sampling distribution of the x bar and hence the t-statistic would be. So if the null hypothesis is true, so if it really is the case that the population mean mu is equal to this hypothesized value m, then this t-statistic has, at least approximately, a t distribution with n minus 1 degrees of freedom. And that result there is what allows us to try to distinguish whether we think the null hypothesis should be rejected or not. Because if it looks like the t-statistic that we've calculated isn't very likely to have been drawn from this t-distribution, then that suggests that we should reject this null hypothesis, because this t-distribution here is only true if the null hypothesis is true. Because that's kind of the intuition of the whole hypothesis testing approach. And basically what we're looking for is whether the t-statistic falls out into the tail. And in particular, because we're looking at an upper tail test, we're looking to see if the t-statistic is far enough into the upper tail of this distribution. And if it is, we will reject the null hypothesis. And the detail of hypothesis tests is to specify what exactly this far enough thing really is. Okay, and we have a choice. Either we reject the null hypothesis if the t-statistic that we calculate here is far enough into the upper tail, or we do not reject the null hypothesis if that's not the case. All right, so we'll illustrate this with an example. Now, I know we've seen some of this in Lecture 13, but it's worth going over this, and then we'll see how it changes once we look at different kinds of hypotheses. This is an example taken directly from the textbook, so it gives a nice example of how you take a problem given to you in words and translate it into a hypothesis testing language. So the question says, a low handicap golfer who uses Titleist brand golf balls observed that his average drive is 208 metres and the standard deviation is 9 metres. I'll just pause there for a minute. There's a whole section in the textbook devoted to doing hypothesis testing for the mean when you know what the standard deviation is. Now the problem is that's just not a realistic situation. So if you don't know the mean, you're not going to know the standard deviation. So in a few of those questions, we will see information being given to us about this standard deviation, which we're just not going to consider. Okay, but this is relevant information here. We'll come back to that. So here we'll just continue on with the question and see where the information is going to be. But this average drive of 208 metres is going to be important information. All right, Nike has just introduced a new ball, and Nike claims that the new ball will travel farther than a Titleist ball. Okay, so there's an important term there. To test the claim, the golfer hits 100 drives with the Nike ball and measures the distance and records them. And the idea is to conduct a test to determine whether Nike is correct. All right, let's start specifying from this bunch of words what are the required symbols and concepts that are required to carry out the hypothesis test. So what we want to test we already know what is the average drive with a Titleist ball. Okay, it's 208 metres. What we want to know something about is what would be the average drive length with a Nike ball. Okay, that's what we're testing, to see whether the Nike claim about the average drive length with their ball is correct. So when a problem is given to you in words like this, it's a good plan before you even start doing any statistics is just to write down what are the relevant parameters. And in this case, the main parameter is simply what is the mean that you want to test a hypothesis about. That's mu here. Mu is the average drive length with the Nike ball. All right, the null hypothesis here is that the average drive length with the Nike ball is the same as what it was with the Titleist ball, which was the 208 metres. So that's where that information is being used. This is giving you the null value. Okay, so if this null hypothesis were true, what that would imply is that whether you use a Nike ball or a Titleist ball, you get the same average length of drive. Okay, so the null hypothesis is that those two things are the same. Now, the alternative hypothesis, and what makes this a one-tail or an upper tail test, is this here. So you've got to look out for these words, which give you the important information. So the Nike is claiming that their ball will travel further, and you're testing to see whether this is correct. So this is one-sided information. You're not testing to see whether the ball has simply a different average drive length. You're testing to see whether it has a longer average drive length. Hence, this is an upper tail test. Now, the golfer hits 100 drives, so that's the sample size. N is equal to 100, and for each of those, the distances have been recorded. Now, in the spreadsheet, here we go. So this is the spreadsheet of the data associated with this question. So these are all the drives. There's going to be 100 of these, right? So basically 100 drives have been hit, the distances have been measured and recorded, and we've come up with all of those numbers there. So they're the 100 drives that are being referred to in the question. So they're the first few of them there, just to give you an idea of what that looks like. And there's the sample and the standard deviation. So I'll actually pause here because we can do this quite easily and just show you if you want to work out the average. Whoops, work out the average, the kind of thing that we've done before quite a few times now of these drives. Then we just need to select that in full range like that, and we get the average of 209.45 there, which is the X bar that's being reported there. And similarly, to get the standard deviation equals stdev sample of this range of observations as well. Okay, and that gives us the 12.15, etc. that's being reported there as the standard deviation. Alright, so that's where those statistics have come from right there. Just going back now to what we're filling in. So we've got the X bar, we've also got the S, and we know that the N is 100, so we have sufficient information to calculate this test statistic right here. Okay, so that's what's going to happen next. Here's the test statistic calculation. X bar, so the M, so I should mention here, the M is this 208, right? So the M is the value which is specified under the null hypothesis, so that gets substituted in here for this M. X bar we've calculated, 209.45. The S we've calculated over here. The N is the sample size is 100, and then we can calculate that thing to be equal to 1.193. And this can always be calculated in here as well. So if we go equals the mean value minus 208 divided by the standard deviation, again divided by the square root of the sample size, which is 100, we'll just put 10 I suppose, and close the brackets, and then that will give us the t statistic there. So that's just showing you how that would be calculated in Excel. It's quite straightforward at that point. Alright, so far so good. Now, how are we going to make a decision? Well, we've talked about measuring how far we are into the tails of the distribution using these p-values, and this is what we'll use in this instance as well. So the upper tail decision rule says we work out, so we've calculated this t-value, t-statistic here now. Okay, that's the 1.19. We know this number. This picture here is giving you what the upper tail test decision rule is. So actually the t here is a different number, isn't it? So what this picture is telling you is we will reject the null hypothesis if the value of t that we calculate falls into this range, such that the probability of getting a drawing from the t distribution which is greater than the value that's observed is in this region, less than 0.05. Okay, so we're dividing up the range of all of the possible t statistics into those here for which this probability is going to be less than or equal to 0.05, okay, and those in this range where the probability is greater than 0.05. So we're expressing the distance that we are into the tail, at the upper tail of this distribution according to this area. Alright, so first of all we can calculate ourselves a p-value using a calculation like this. So the definition of the p-value is p is equal to the for an upper tail test, importantly. So the way that we calculate this p-value is different for an upper tail, a lower tail, or a two-tail test. Okay? So for an upper tail test, the p-value is the probability that the t distribution is greater than the observed t or calculated t statistic, and that can be calculated as using this formula here in Excel. So the p-value, we calculate that number, then the p-value is found by the t distribution. Now this RT thing here, or this RT thing here, is talking about, is specifying the right tail of the distribution. So we didn't see this in lecture 13, but it's a quick way to get to the p-value for an upper tail test. So if you use this right tail version of the t-list command, then it immediately calculates the probability above the value of the t statistic that you have calculated. Okay, so you just literally type this in. So the degrees of freedom that we just went by before, that 99, is n minus 1. Okay, so 100, sample size of 100 means you put 99 in there for your second argument to the t distribution command, and it calculates a p-value of 0.118, which is the area above the t statistic. So the probability that the t distribution is greater than 1.193 is 0.118. The decision rule is we will reject the null if the p is less than 0.05. Well, the p is not less than 0.05, so we will not reject the null, and the evidence is not supporting Nike's claim in this case. And that's where we'd finish the hypothesis test. That answers the question using the p-value decision rule. All right, coming back to this picture here, this was our decision rule that expressed everything in terms of the areas under the curve, this kind of probability. Now we could just as easily express our decision rule, as you can see, in terms of the values of the t-statistic itself. So rather than working out areas under the curve, we could simply ask, well, what is this value? And compare the t-statistic directly to whatever this value is. And if the t-statistic is greater than this value, we reject the null. And if it's less than this value, then we don't reject the null. The question is, what is this value? In other words, what is the value of t for which this probability is exactly equal to 0.05? And this is how we would work this out. So the value of t, which gives us 0.05 up here, is the same value of t which will give us 0.95 down here. Okay, because these two, the area under the entire density function has to be 1. So these two probabilities have to add up to 1. So finding the value of t, for which this upper probability is 0.05, is the same as finding the value of t, for which this lower probability is 0.95. And that's relevant because this is what the Excel command directly calculates. Okay, so here's the calculation here that's done in Excel. So if n is equal to 100, in other words 99 degrees of freedom, then you can calculate the t critical value, it's called, by t dot inv. So this is the inverse of the t distribution. 0.95 is this probability here, and 99 degrees of freedom, that returns the value of that dividing point. That critical value is 1.6604. Okay, so we could just prove to you that it actually works. T dot inverse and 0.95 and 99 degrees of freedom gives us that value that I'm alleging there. Okay, so that's how you can get those critical values directly from Excel. So the decision rule, which before we expressed in terms of these areas under the curve, these probabilities, can now be expressed in terms of this value here. Important thing, this value here is different for each value of n. Notice that we had to use the degrees of freedom to calculate this critical value. So if you've got a different sample size, you would calculate a different critical value corresponding to that sample size. There it was. So we call this number here the critical value. Okay? All right. So here is how it works. Okay. The critical value. So we have this is going to be our notation for the critical value. So there's lots of things in this stuff that's called t, and it's important to keep track of what t concept we're talking about. So when you see a t with two things down here, an alpha, which is denoting this significance level, how far we are into the tail of the distribution, and which we'll talk about more pretty soon, and n-1, which is the degrees of freedom. So when both of those things are included as subscripts to the t, that's telling you that we're talking about a critical value. Okay. Whereas this t with an n-1 and there's no alpha included there, this is just simply referring to the t distribution with degrees of freedom of n-1. So you can think of this thing here as being a random variable, and this thing here as being a critical value, such that the probability that the t distribution is above this critical value is equal to alpha. So this probability statement here is referring to this probability statement right here, where in this case we're talking about alpha being 0.05. In the golf example, as we saw, the critical value is 0.16604, that we calculated before, and the t-statistic that we calculated was 1.193. So you can see that in this case, the t statistic is less than the t critical value. So in other words, we're talking about a situation here where the t statistic is somewhere around about here, right, in the green area, where we're not rejecting the null hypothesis. It's below 1.66, okay, somewhere down here. As a result, we do not reject the null hypothesis at the 5% significance level. And we come to the conclusion, the same conclusion that we saw before from the p-value, which is that the evidence does not support Nike's claim about the increased distance on average. Now that's the same conclusion that we got from the p-value and the critical value rules, and that has to be the case. So the p-value and the critical value decision rules are exactly equivalent. Okay, one is derived from the other, as we saw. So you cannot get different answers from the two. If you do, that's just a sign that you've made a mistake. So it's a useful check when you're learning this stuff to carry out both versions of the hypothesis test, just to check you know what's going on and that you do get the same answer in each case. This here is just basically a summary. So if you want a summary of what the decision rules look like and what you have to do in order to implement them in Excel, then this one overhead here tells you what you need to know. Okay, if you want to do, or if you're asked to do, you need to know how to do both p-value and critical value versions of tests. So if you're asked to do a p-value version of a test, then this is the relevant information. Okay, so the distance into the upper tail is being measured by the probabilities, and the p-value that's calculated is the probability of getting the t distribution above the t statistic that you calculate. So this thing here for an upper tail test is the p-value, and that p-value can be calculated by this command right here in general, this tdist.rightTail or upper tail. Okay, you put in your statistic, you put in your degrees of freedom, and that will return to you the p-value, which you can then compare to alpha, which maybe 0.05 or whatever significance level is specified in the question. The default is 0.05, so if you're not told what the significance level is explicitly, then you can assume that it will be 0.05. So the decision rule is very easy once you've done that. If the p is less than the alpha, you reject the null, and if it's not, you do not reject the null. In the case of the critical value versions, then you calculate your t statistic and you have to work out your critical value using this kind of calculation that we did just before, using the t inverse function in Excel. Or equivalently, you can look up the critical value from a table, and this is something that you should know how to do, and it's the kind of thing that would be necessary in an exam, for instance, given that Excel won't be available to you in an exam, but a table of critical values will be. And the table looks like this. This is taken directly from the textbook, and it's the table that you should know how to use. And the way that you read this is, so here is this little distribution that it gives you in the textbook itself, and this shaded area is, so A for area, and TA is the value of T, which corresponds to that area. So this is precisely what we want for an upper-tailed critical value. So if you want to do a test at the 5% level of significance, let's say, then 0.05 is the column that you want. And then it's just a matter of finding the degrees of freedom, or at least the nearest degrees of freedom. So in the case of the golf example, there were 100 drives, so the degrees of freedom was 99. So 99 is not there, but 100 is there. And you can see, incidentally, the numbers. So this is the number we want, 1.660, which is what we found, to 3 decimal places at least. You can see that the critical values don't actually change very much once you get into these higher degrees of freedom anyway. So from a practical perspective, you're only changing things at the 3rd decimal place. It doesn't make a huge difference. If 95 and 100 is included in the table, it doesn't really matter that you don't have 99. You just use the closest one and that'll be fine. So this 1.660 is the value you would look up from the table for that golf drives example and use that as your critical value here. Okay. So you can either calculate it in Excel exactly or look it up in the table.